faithfully conveying value, interpreting global masterpieces. Hi, this is Sally's Book Club. Today we'll explore Stephen Hawking's masterpiece, A Brief History of Time. 1. Since its 1988 publication, this book has been translated into over 40 languages, with tens of millions of copies sold. Given its massive popularity, many wonder what groundbreaking ideas Hawking actually presented. If you've struggled to get through the book yourself, let today's breakdown guide you through this masterpiece. Before diving into the content, let's understand its publishing context. Hawking mentioned in the acknowledgments that he aimed to create an accessible book about space-time to answer one fundamental question. Where did the universe come from? Some might ask, why is it called A Brief History of Time? Wait, isn't this about the cosmos? The original title was actually From the Big Bang to Black Holes, A Brief History of Time. Summarizing humanity's evolving understanding of the universe and time itself. Hawking began researching black holes and cosmology in the 1960s, witnessing and contributing to modern cosmology's development. The revolutionary rethinking of fundamental concepts like cosmos, space, and time forms the most fascinating aspect of both this book and cosmology itself. Now that we've covered the publication background of A Brief History of Time, 1. Let's explore what this book actually reveals. How can we truly understand it? The 130,000-word book contains 12 chapters, which we'll analyze through 3 key sections. First, humanity's evolving understanding of the universe. Second, the history of physics development, the foundation for understanding modern cosmology. Third, Hawking's groundbreaking research on black hole properties. Let's begin with humanity's cosmic understanding. 4 major theories emerge sigillally: flat Earth, geocentrism, heliocentrism, and infinite universe theories. Initially, humans believed in the flat Earth theory, which aligned with primitive observational evidence. As technology advanced and human knowledge expanded, the spherical Earth concept replaced this ancient belief. Over 2,000 years ago, geocentrism emerged. Supported by philosophers like Aristotle and Ptolemy, it proposed Earth as the universe's center, with celestial bodies revolving around it. This perspective aligned with humanity's astronomical observation capabilities at the time. In the 16th century, Copernicus identified logical flaws in geocentrism. Noticing discrepancies between geocentrism and astronomical observations, he proposed heliocentrism, positioning the Sun as the cosmic center, with Earth being its orbiting planet. Galileo and Kepler further verified, refined, and expanded heliocentric theory. A century later, Newton built upon Copernican cosmology through gravitational theory, solving dynamical questions about solar systems and stars. From gravitational principles, Newton deduced an infinite universe theory, suggesting boundless cosmic expansion. Humanity's cosmic understanding evolved alongside physics, as cosmology studies celestial mechanics, while physics reveals motion's fundamental laws. Therefore, in Part 1, Hawking dedicates 4 chapters to physics' historical development. This section covers classical physics, represented by Aristotle and Newton, followed by 20th century pillars, general relativity, and quantum mechanics. You'll discover how physics and astronomy mutually influence each other, with physical advancements reshaping cosmic concepts. Let's first revisit classical physics. Aristotle's kinematics posited that force maintains motion, with objects remaining stationary unless acted upon. Thus, in his geocentric model, Earth rests motionless at the cosmic center, while celestial bodies orbit in concentric spheres. But what propelled these celestial movements? Aristotle hypothesized a prime mover beyond the stellar sphere, the famous unmoved mover. Who was this mover? Unknown. Newton's law of universal gravitation and three motion laws probably challenged you in high school physics. Their significance lies in quantitatively explaining motion mechanics while expanding cosmic discussions beyond our solar system. Regarding the cosmos, Newton believed star-composed universes should remain stable and unchanging. For millennia, the seemingly unchanging night sky suggested stars existed in static equilibrium. Newton believed his law of universal gravitation applied to stars. Just as gravity makes apples fall, it causes all mass-bearing objects to move toward centers. He concluded, the universe must be infinite and centerless. A finite universe would collapse under gravity's pull, destroying cosmic stability. In infinite space, gravitational forces from all directions balance perfectly, maintaining stellar stability. Newton's static infinite universe model proposed 1. Flat, endless space, 2. Uniformly flowing time, 3. Matter moving through rigid space-time framework. Before discovering stars' billion-year lifespans, they appeared eternal to human observers. Newtonian physics couldn't predict relativistic time dilation at near light speeds, phenomena beyond daily experience. Newton's cosmic model dominated for 2 centuries until new physics and astronomy discoveries dismantled it. Einstein's general relativity emerged as a revolutionary replacement. In early 20th century, Einstein established light speed invariance as special relativity's foundation, unifying space-time concepts. After a decade's work, Einstein incorporated gravity into relativity theory, formulating general relativity. Space-time isn't flat, as Newton thought. Massive objects warp its fabric. Newton described flat space, where Earth orbits Sun through gravitational pull. Einstein revealed the Sun's mass curves surrounding space-time. The cosmic space-time structure itself exists as curved geometry. Einstein fundamentally reinterpreted gravity's nature through space-time curvature. He proposed that space-time curvature creates gravity, the core concept of general relativity. Using general relativity, physicists Friedmann and Lemaitre discovered space cannot remain static. In 1929, American astronomer Hubble confirmed the universe's ongoing expansion. The other pillar of 20th century physics, alongside relativity, is quantum mechanics. It also underpins new developments in cosmology. Before discussing quantum mechanics, let's meet photons, electrons, and atomic nuclei, the microscopic building blocks of matter. Photons constitute light. Electrons orbit nuclei to form atoms which combine into molecules, matter's fundamental units. Quantum mechanics reveals microscopic particles have quantized discontinuous energy states. Microscopic particles obey radically different rules than macroscopic objects. Macroscopic motion becomes predictable with precise measurements similar to tracking someone through surveillance cameras. Newtonian physics, therefore, follows deterministic principles. Quantum discoveries shatter determinism through the uncertainty principle. We cannot simultaneously measure all particle properties. For example, measuring photon velocity. Probing particle properties requires using detection particles like photons, which inevitably disturb the measured system. This uncertainty stems from particles' inherent probabilistic nature, not measurement interference. Photons, electrons, and atoms fundamentally exhibit Bayesian randomness. Quantum mechanics and relativity combined revolutionize cosmic understanding. Quantum research reveals microscopic laws governing stellar interiors. For instance, hydrogen nuclei fuse into helium through nuclear fusion at stellar cores. This process releases energy as light radiation. Relativity governs macroscopic phenomena. Massive objects curve space-time. This curvature manifests as gravity governing celestial motion. Einstein fundamentally reinterpreted gravity through space-time geometry. Thus, scientists theorize the universe originated from a Big Bang, followed by continuous expansion. During this process, microscopic particles form celestial bodies like stars and galaxies, with stellar evolution creating diverse elements. These elements eventually coalesced into new stars, planets including Earth, forming the core narrative of Big Bang cosmology.